College trig, here's 8.3, complex plane. We're going to break 8.3 into two sections today, so this is 8.3a. So recall from our complex plane that when we graph things that our horizontal axis is our real axis corresponding to our real value, and our vertical axis here is your imaginary axis corresponding to your y. So also remember, when we were in college algebra, when you saw this symbol here, that was called absolute value. Well, remember, absolute value is your distance away from zero. So if you have a point here, your distance away from zero is this, okay? And in this book, this is called your magnitude of z, the size of it. So don't get it thrown off. So remember from your work before that to find that value, again, right triangle trig, this is your x parameter, this is your y parameter from your complex number, your real and your imaginary. To find that magnitude, you just have to use your Pythagorean theorem, and you get x squared plus y squared equals z squared. Okay, so make sure you have this equation for finding the magnitude of z. So this is a notation you'll see in our book, and it's really no different. The idea here is, remember that when you have a bar above z, okay, that means it is a conjugate. And all you have to do for a conjugate, if z equals x plus yi, z bar is equal to x minus yi, where the sign is changed. So the nice thing about the conjugate, if you remember, is that you have, when you multiply them together, so let's just look at an example. If I have 2 plus 3i, and the conjugate is 2 minus 3i, when I multiply these together and double distribute, I get 2 times 2 is 4, minus 6i, plus 6i, and then I get minus 9i squared. Well, notice that this middle terms drop out, and we get 4 minus 9i squared. I squared is -1, so we get 4 plus 9. Well, this is just 2 squared plus 3 squared. Okay, so in order to do this, so 2 squared plus 3 squared, that is z times z bar. In order to find the magnitude, so if we're thinking about graphing this as 2 on the real axis and 3 on the imaginary axis, and we're trying to find this magnitude, z bar, that you do 2 squared plus 3 squared, and then you square root it. So that's where this equation comes from. It's just z times z bar, and then the square root. You square root this answer, just like the Pythagorean theorem, and you get your magnitude of z. Okay, so that's how we get that equation. So remember, in your Cartesian form, you had your real part here represented as your x, and your imaginary part represented with your y. You know that because it's in front of your eye. So now we're going to start graphing these on your polar form. Okay, so the conversion for this is your equation. R cosine of theta, remember, this is the equation that we had before. X was equal to R cosine theta, Y is equal to R sine of theta. So as we're trying to graph our complex numbers in the polar form, we use our same XY conversions, and we get this. They both have an R, so we can factor that out here. And we see that to write a number in polar form, a complex number in polar form, we get that it looks like this, where R is our radius, or our Z magnitude, and then cosine of theta plus I sine of theta, where this corresponds to your X, that's your Y. All right, so blending a lot of ideas here, graphing on a imaginary plane joined with graphing on a polar form. So let's look at going in between the two forms. So you can see here why the magnitude is the same as r. Notice we go ahead and put into the equation x squared plus y squared and take the square root. By doing so, the r squared are factored out, and then from there, after we factored out our r squared, we get r squared on the outside, cosine theta plus sine squared theta. That should ring a bell. That's one of our most famous identities, Pythagorean. And then that's just 1. 1 times r squared is r squared. Square root of r squared is r. So you can see why the magnitude is r. All right. So the first thing that we're going to work here is rectangular to polar. Next, we'll go from polar to rectangular. So what I want to do here is first I want to figure out what my radius is. So looking at this, thinking about my triangle, this is 3, this is 4, and without, so negative 3 squared plus 4 squared, square rooted. This is square root of 25, which is equal to 5, is our Pythagorean triple. So this is equal to my r, okay, or the magnitude of z, okay, the magnitude of this distance from here to here, okay. So remember, my polar form is going to be r cosine of theta plus I sine of theta. So I know my r, that's 5, cosine, don't know my theta yet, plus I sine, don't know my theta yet, and I'm in there. So to get my theta, I got to recognize that this is a theta that I want. And we got to be careful here because, again, this is a quadrant 2 angle. So if I find, depending on if I use sine or cosine or tangent, it's going to give me a different quadrant angle. So going off of what has been familiar to us from the last bit of work we've been doing, we know that tangent of theta is equal to y over x. When I do inverse tangent of y over x, I get my theta. Well, my tangent of, sorry, make sure this is clearly spread up, my y, which is 4 over negative 3, and what am I going to get? Well, I'm going to put this into my calculator, and I'm just going to be in degrees, so I check my mode, and I'm in degrees, and I'm going to do inverse tangent of 4 over negative 3, and I get this angle, okay, 53 degrees. So recognize that that is a quadrant 4 angle. Negative 53 degrees is going to be an angle down here because I'm going, so this is negative 53 degrees. This angle is the same here as it is here, 53 degrees. So if I want to go ahead and find this quadrant 2 angle, so finish this out, I know that this gives me an angle of negative 53 degrees. To get it into a quadrant 2 angle, depending on how you think about it, we've got to make sure we understand we just don't do the principal angle, but I'm going to do pi plus my negative 53 degrees. Sorry, not pi, we're not dealing with radians, so it's 180 degrees, plus a negative 53, and I'm going to get 127 degrees. Okay, so the last thing I do is put 127 into those where my theta is, and I'm done. This is polar form of a complex number. What I want to look at here is how the book walked through it, and notice that here, when they, instead of doing tangent, they use inverse sine. So recognizing that they had 4/5, they know that it's a quadrant 2 angle. Well, they use sine because they know it's going to be positive in that quadrant. Well, you get your principal angle of 53.3 degrees, so they still have to do the theta minus that 53 degrees to make sure you get a quadrant 2 angle. Grading a lot of these quizzes tonight, I recognize that a lot of us are still struggling with this idea that you get a principal angle in your calculator, but we're not converting it to the quadrant that this needs to fall into. Clearly, we know that this needs to be over here, so make sure that your angle corresponds to the correct quadrant. Okay, so next what we have to do is we got to go the other way around. We got to go from polar to rectangular. Okay. All right, so going backwards, again, we just need to, I think a picture is always positive. So 330 degrees, we're going to be over here somewhere, and we have a radius of 2. So really what I'm trying to find is this x and y coordinates here. Well, what's nice is I know that this around here is 330, and I know from my unit circle that the cosine of 330 is equal to square root of 3/2, and my sine of 330 degrees is equal to 1/2 negative, because we're below the axis here. So I know I have a negative y there, a positive x. So from there, I see that to convert it, I'm just going to do x plus yi is equal to 2 times the cosine of my theta, square root of 3/2, plus my 2 times negative 1/2 I as my imaginary part. And notice I distributed both of them are being multiplied by 2, which is really just a scale factor there, and we get square root of 3 minus 1i. And now that is in rectangular form. There's my x parameter and my y parameter. So we need to make sure we can go back and forth from polar to rectangular and rectangular to polar. Here's the bookwork. Also with most number systems, just like when we were dealing with complex numbers, we're going to have to multiply numbers together, and we're going to have to divide numbers together. So these are the formulas you're going to get here. Notice that Z1 and Z2, it's just a way of denoting two different complex numbers. To multiply them together, you do R1 times R2, and then it's just cosine, and then you add the angles. Sine, add the angles. Okay, division is not too much of a stretch. Well, you're going to divide your r's, but instead you're going to do theta 1 minus your theta 2, theta 1 minus your theta 2. Notice the similarities between these equations, but more importantly, definitely notice the difference. We got different signs here and different ways that we deal with our magnitude or our R value, but everything else more or less lines up the same. We'll look at the proof of this tomorrow in class, but let's go ahead and see how an example of this works out. So we're given 2 points. Don't be thrown off. This is Z2 and Z1. The fact that it's called Z and W is just two different points. So if I want to do Z times W, I'm going to use my formula, and I know that Z times W is going to be equal to R1 times R2, so 4 times 6, and then I'm going to have the cosine of the sum of these two angles. Sum, the order doesn't matter, so I get 160 plus I sine of 160. Just clean it up a little bit, and I get 24 times the cosine of 160 plus I sine of 160, and we leave it there. That is your polar form of an equation in complex plane. Okay, so let's go ahead and try dividing by. So dividing by, do in green, use my equation, and it's going to be Z over W. Remember, order does matter in multiplication, that W over Z, those are not equal. So we got to make sure of the order in this. So I'm going to have my Z as my numerator. So that is going to be 4 over 6. And then just like with subtraction here, order is going to matter. So I'm going to do cosine of 40 minus 120 plus I sine of 40 minus 120, and then clean it up, get it ready for church. So 4 over 6, we get 2 over 3, and then cosine, notice smaller number subtracted a bigger number, we're going to get a negative answer here, cosine of negative 80 degrees. Okay, plus the imaginary part, sine of negative 80 degrees. And that is an appropriate answer, a good answer, not a great answer. The answers in the back of the book we're going to recognize will always be on an interval from 0 to 360 degrees. So this is an acceptable answer, but if we're checking the back of the book, we want to make sure we understand that negative 80 degrees is down here. So if I want the actual positive angle here, and this is negative 80, it's going to be 360 minus 80 degrees, which is going to be 280 degrees. So a better solution is 2/3 cosine of 280 degrees plus the imaginary sine of 280 degrees. All right, so make sure you have your formulas down in your notes. We're going to be using these a lot tomorrow in the problem sets. Make sure you have, if you have questions, you're highlighting them now in your notes so you come to class tomorrow ready to ask me those questions. Have a great evening.